These are solutions to review B for quarter one. So first we have to sketch some graphs of the common function and its derivative. So x cubed, if I exaggerate a little bit here, so this is our f of x, and we want to make very clear that we have this saddle point. The derivative hits 0 only at one point, but otherwise our graph is rising, hits 0, and then it's rising again. So our derivative is always above the axis, except at 0. And of course we know by the power rule that f prime is going to be our parabola x squared. So this one is easy to graph visually, and we also know the equation would be 3x squared. All right, the cube root of x, if I do my original graph again in red, the cube root, here's our f of x graph, and its derivative, first let's think visually. Here we've got a vertical tangent, so our slopes are very close to 0, and then they get very positive. So here our slopes are above 0 and they zoom up to infinity. And on the other side, our slopes are also positive. They start out at positive infinity, and they always stay positive. So visually, this appears to be our graph of f prime. And now let's do the formula using the power rule. We would bring down the 1/3 power and get x to the negative 2/3. In other words, 1/3 cube root of x squared. So we can see that our red graph was was odd, and our green graph is even. So that might be worthy of note here. We started with an odd function and we ended up with an even derivative. All right, in number 3, our common function here shifted 3 units to the right, so this would be at +1, -1, and at 3. So there's our graph of f of x, and its slopes are always 0 except one place where they do not exist. So the derivative should be a horizontal line. F prime of x equals 0, except x cannot be equal to 3, where the derivative doesn't exist because there's no point of tangency. All right. Now let's interpret some graphs, always a little bit more challenging. If the graph shown is f prime, find the intervals where the original function would be increasing. So f is increasing when f prime of x is greater than 0, and that appears to be on the interval from negative infinity if this graph continues, and that's what I would take it to be, to -1, and it is again positive from 0 to, this looks like 3. So from 0 to 3. All right, if the graph shown is f prime again, give the x values where f has a local minimum. Well, a function has its local minimum when it goes through a valley. So in other words, when it is decreasing and then increasing. So what does that mean? Decreasing, f prime of x changes from negative to positive at x prime changes from negative to positive at 0. So f has a local minimum at that point. because negative derivatives mean that the original graph was falling and positive derivatives mean the original graph was rising. All right, and number 6. If the graph shown is f prime, give the intervals where f is concave up. Well, you might find it easier to think about this. F double prime greater than 0 is concave up. So when is f double prime greater than 0? When f prime of x is increasing. When f prime of x is increasing. So f prime of x is increasing from, we'll say, negative 1/2 to, does that look like 1.5? All right, so f is concave up when f prime of x is increasing, and that we're going to say is on negative, open interval, negative 0.5 to, what did I decide that was? I don't know if that's 1.5 or 2. I'm going to go ahead and say 1.75. So you can decide what that looks like. Number 7, if the graph shown is f double prime, so let's make sure we switch gears. If this graph is f double prime, give the intervals where f is concave up. So f is concave up where f double prime of x is greater than 0, and that would be on negative infinity to negative 1 and 0 to 3 again. So second derivative positive means concave up. That's the same thing as saying when f prime is increasing, by the way. All right, number 8, if the graph shown is already f prime, give any x values where f has an inflection point. Okay, for me it's much easier to say that we're looking for places where does f double prime change signs, and that, thinking backwards, is where f prime changes from increasing to decreasing or vice versa. So concavity is going to change when our first derivative changes from increasing to decreasing or decreasing to increasing. So does that look like negative 0.5? And oh, this was the point I couldn't decide about, so I'm going to call that 1.75 again. What do I want to say here? F has inflection points at x equals negative 0.5 and at x equals 1.75 because f prime of x changes from increasing to decreasing or vice versa. Can you say where it has a local max or a local minimum? I guess that would be okay, but the problem is you might have some corners, so you might want to think twice about that. All right, number 9. If the graph shown is f double prime, give any x values where f has inflection points. Well, that's easier because inflection points are where does concavity change. So concavity changes at inflection points, and that's easy for me to tell from f double prime. When f double prime of x changes sign, and that would be at negative 1, 0, and 3. F will have an inflection point. Now, you could write your sentences different than I did here. but I think we've got the correct places. All right. Now we're going to read some values from a graph of two functions. So if h of x is defined to be the difference of f of x and g of x, then how can we find the derivative? Well, this is just our difference rule. The difference of a sum, the derivative of a sum is the sum of the derivatives. The derivative of a difference is the difference of the derivatives. So all we need to do here to find h prime of 3 is say, well, what is f prime of 3? And subtract g prime of 3. So we're looking at the graph and we want to read the slopes. So at 3, f has a tangent line here. Looks like our rise is 1, 2, 3, 4 squares, and our run is 1, 2, 3, 4 squares. So it looks like f of 3 has a slope of 1, and g prime of 3, let's see what our tangent line has a slope of here. It looks like we're going down 2 squares and over 4. So does it look like this has a slope of negative 1/2? So be careful about subtraction. So I think we should have 3/2. Oh, I don't want to go back and change that work because I think it was right. But I just looked at my notes and I just did the derivative at positive 3 instead of negative 3. So let's switch gears and let's do that again. H prime of negative 3 by the same idea. Sorry to waste your time. So we want at negative 3 here we've got a slope of 0 for f prime. And for g our slope is down 1 over 3. So it looks like negative 1/3. So I think we should have positive 1/3 for our answer there now that I'm doing h prime of negative 3. All right, let me erase these notes, and next we have to do a quotient rule. So let's write our quotient rule here, and then we can plug in our values. So we would have low function times derivative of the high function minus the high function times the derivative of the low function all over the low function squared. And now we want to put negative 1 in for our x. So let's carefully go through. First I want f of 1. F of 1, not the derivative, but f of 1, so that would be a y-coordinate of 2. And then g prime at, oops, I'm doing the same thing again, aren't I? Negative 1, not at positive 1, happens to be the same thing. F of negative 1 is 2, so I'm okay. G prime of negative 1, it looks like we have a slope of rise 1, run 2, so a slope of 1/2. G of negative 1, G of negative 1 looks like a negative 1/2. And then f prime of negative 1/2, so our slope here is a negative 1. All divided by f of negative 1. We've already done f of negative 1 is 2, and then we're going to square it. So let's see if I have some arithmetic correct here. So we'll have a 2 times 1/2 is 1 minus a 1/2. So we'll have a 1/2 divided by 4. So I think we'll come up with a 1/8, but let me stop and check my arithmetic. I don't see anything wrong there, so we'll proceed our product rule. To do the derivative of a product, we take the first function f of x times the derivative of the second function plus the second function g of x times the derivative of the first. And now we want to just put 2 in for those x's. So we want to do f of 2. F of 2, let me make sure I'm reading correctly. F of 2 appears to be a 3. And g prime of 2, we're looking at the slope now here. So it looks like we're going down 2 over 4, so negative 1/2. And g of 2 is negative 1. That's just the y coordinate. And f of 2 is our slope here, which is positive 1. So we have a negative 3/2 minus 1. So should we have a negative 5/2? Again, let me stop and check my arithmetic before I move on. I don't see any arithmetic errors. All right, pressing on. Find the equation of the tangent and the normal. So let's find out what is our point of tangency. That would be putting 2 into our function. So that would be an 8 minus 4 or 4. So 2, 4 is our point of tangency. And let's find our formula for f prime of x, 3x squared minus 2. So particularly, our numeric derivative at 2 would be 3 times 4 or 12 minus 2 is 10. So this would be the slope of our tangent. So our tangent line, and you need not show this work. You guys are perfectly welcome to skip steps here. So y minus our y coordinate equals 10 times x minus our x coordinate. And for our normal, we've got the same point of tangency, but our slope would be negative 1/10. All right, some true-false. Make sure you're looking for the counterexamples. One counterexample makes it false, of course. All right, f of x equals absolute value of x plus 1. Well, we know absolute value is an even function, so moving it up 1 unit is still an even function. Now, notice that if we had put that 1 inside the parenthesis, that would shift it over off of the axis. So this would not be even, but a vertical shift is even, so that would be true. If our second derivative at 11 is equal to 0, then does that mean that we've got a point of inflection? Well, that's not necessarily true because f double prime has to change signs. F double prime must change signs to get an inflection point, and it could be a bounce point. So a typical example would be if we had a 4th degree polynomial, which is always concave up, but right here at 11, for example, we might get a first derivative of 0, and then the second derivative would also be 0, but our second derivative would look like a quadratic. So it would still have a bounce point. It might not cross over the axis. So hitting 0 is not enough for an inflection point. It has to, f double prime has to change signs. If f is continuous over this interval, then does the limit exist at 1? Well, 1 definitely falls into the continuous interval. So remember that if a function is continuous, then the limit exists by direct substitution. If f is differentiable over an interval, then is it continuous? Well, if it's differentiable, it means we were able to find a derivative, and a derivative requires a point of tangency everywhere. So we have a theorem that if a function is differentiable, then it is continuous. So that is also true. 18, however, says if it's continuous, does that guarantee that it's differentiable? And the counterexample is it could have a corner. So corners are still continuous. So for example, from -3 to 7, we could have our absolute value function. And here f prime of 0 does not exist. So even though the function is continuous, does not guarantee that it has a derivative because it could have a corner. All right, 19. If our first derivative is 0, so that means horizontal tangent, and our first derivative is negative from 1 to 7, so that means f is decreasing when the first derivative is negative. And then f prime of x, again is less than 0, so careful. Notice these both say less than 0. So f is decreasing again on the other side. So how could that happen? Well, at that point 7, 9, we could have a function that is decreasing and then hits a horizontal tangent and then decreasing again. So saddle point is our counterexample. So that doesn't read the way we would expect it to. All right, had it changed from decreasing to increasing, then it would have been a local minimum. So I think we would have had a question about that one regardless. All right, number 20. If our second derivative at 7 is equal to 0, then do we necessarily have an inflection point? Well, that's the same as the question up above. I think it was number 15. F double prime of x must change signs. Just hitting 0 isn't good enough. So you guys know all the time here that we could have functions. We could have functions that hit 0, but they don't cross over the x-axis. They might bounce there. So that is not enough. F double prime has to change from positive to negative or negative to positive to give us an inflection point. Okay, one more. If the limit as we approach a from the left side of f of x goes to infinity, then f of a is a cusp. Well, it doesn't even say that this is f prime, does it? If that said that it was f prime, that still wouldn't be enough to get a cusp. So here all we know that we have is a vertical asymptote. But remember, even for a cusp, the first derivative has to change, has to go to negative infinity from one side and positive infinity from the other side. So 21 is definitely false. And I think that was it.